to the second session, and our first talk is from one of our sponsors, Atkins Global. Our speaker is Chris Sampson, who's going to talk about static analysis and formal proof for software systems using the MALPAS Toolset. Chris leads the software safety group within Atkins. He's a highly experienced software safety consultant with over 20 years of experience across a wide range of software lifecycle activities with an emphasis on high integrity and safety critical software. He is currently providing advice and guidance to high-profile projects in the defence, nuclear and rail industries of safety critical systems. I'll hand over to Chris.
Okay, thank you. What I wanted to talk about today is verification by static analysis. I see from the agenda I'm not the only person talking about static analysis today, so do forgive me if there's any repetition from previous presentations. Really, what I want to get across here is a general overview of what I mean by static analysis, how it can help with verifying your software systems, and the different types of static analysis that are available, different tools, different approaches to static analysis, different objectives, different reasons for using it. So it's a bit of a high-level introduction to the subject, with, at the end, a few slides with some examples on. So there is some code, so hope everyone's awake after their coffee break, and we'll take some questions at the end as well. So, what do I mean by software verification? Now here's a useful definition from the IEEE, which is, I think, the best one around. It's quite interesting that there's many definitions of software verification in the standards and in the quality manuals, and there's quite a broad range and different number of differences between them. But this is what I understand by it: the process of evaluating software during or at the end of the development process. So that's important. It's not just an activity that you do after you've written the code. It's something that you do throughout the whole development process. And the objective of it is to determine whether it satisfies the specified requirements. So for each stage in your development, whether you're going from the requirement spec to a software architecture down to a low-level design to coding, and even the coding through the compilation process, each of those stages ought to be verified, and the process of making sure that some activity that you've done corresponds to the previous stage of the activity and the requirements for the activity, that's all verification. It's a different activity from validation. Validation is all about making sure that you've developed the right system, that the final system that you've developed does what the user wants it to do. Verification is saying, we've written something down, we've done some activity, and now we're going to check that that activity that we've done meets the requirements for that stage. So it's important to separate out verification and validation. And the static analysis approach that I'm talking about today is all about verification. It won't tell you whether you've developed the right system that the user was looking for, but it will tell you whether you've developed a system which meets the requirements. Now, there are a number of verification techniques kicking around, and the two main ones that people use are dynamic testing. This is your traditional software testing, where you write some test cases or a test specification, you execute it on the software, get some results, and check that the results are what you expect. We've all done that, I expect, in the room, and that is the tried and tested traditional approach to verification. But there's also static analysis, and what I mean by this is an activity that analyzes certain properties of the code or the design without actually executing it. So most of the static analysis tools I'm going to talk about today operate at the source code level, but there's also things like model checkers around these days which work on some sort of abstraction of the design level and can prove properties at that level without getting tied up in all the complexity and the detail of the source code. So my first observation, why use static analysis? We've been doing testing for 60 odd years in the software industry. Why come along with something different? And the argument that I put forward is that for any complex piece of software, and it doesn't take very much for software to get complex very quickly, it is not possible to test all of the paths through the code or all of the combinations of inputs. I've got a couple of examples here that I've been working on quite recently. I was doing some verification of a level crossing application last week even. And this bit of code had 187 Boolean inputs. The code wasn't especially well written, I must say, and all of the outputs depended upon all of the inputs for some reason that we haven't quite got to the bottom of. But I stuck the numbers in my calculator and worked out there are 10 to the 56 possible combinations of these Boolean inputs. Now that's going to take quite a while to exhaustively test. And I didn't work out whether there's enough time before the universe dies to do that, but we're talking very, very large numbers there, and it's clearly not possible to exhaustively test that software. A nuclear power application I worked on a few years ago had 20 sequential if statements. Perfectly good bit of code, actually. There was a very good reason why the design had gone that way. If you actually work out how many paths through the code, so how many combinations of all the true and falses in those if statements, you get over 1 million paths through the code. And again, I would argue that's going to take quite a while to actually test all 1 million of those, and possibly is not affordable, not achievable. So, I mean, these are not unreasonable pieces of software where these problems occur. So testing is expensive to exhaustively test, and what really happens in practice is that people don't test all of the paths through the code, they don't test all of the combinations of the inputs, and therefore you may get some reassurance from a successful test that you think, great, this bit of code works okay, but it doesn't. There are latent faults remaining in that software after testing that may well come back to bite you when that piece of software goes into operation. Now, most of the work I do, as we heard in the introduction, is in the safety critical area, and we can't afford to have latent faults in there that are going to come and bite us once the system's in operation. I don't want my level crossing to open when the train's coming. I don't want my nuclear power plant to go bang. I don't think anyone else would like that either. So for certain applications, certainly in the safety area, we need to get rid of these bugs, and we need to have a better technique for verifying our software. I also make the argument that for standard commercial software, some of these static analysis techniques these days are pretty cheap and quick to run and can give you very high levels of confidence in your software, and are probably worth doing anyway on commercial software. So these techniques are not restricted just to safety and high integrity applications. They've got some real benefit for commercial software as well. So what I mean by static analysis, I very black and white this. So dynamic testing is when you actually execute the software. Static analysis is when you don't execute the software, but you analyze various properties of it. And I say there are two main objectives. Firstly, what I call integrity checking. This is a phrase that comes from the nuclear sector. But what they really mean here is checking for an absence of runtime errors. So these are things which could throw exceptions in your software. They are the types of error that you're looking for are known in advance. They're things like uninitialized variables, divide by zero errors, and all of those are called integrity checking. Second type of static analysis is what I call functional analysis, and this is making sure that the code and the specification are consistent. So it's not just will my software crash, but will it actually do what the requirement asks it to do, and that's a functional analysis. We come on a little bit later to what that actually means when you're doing static analysis. When you're looking at the tools available, there are certain tools which will only do the integrity checking, and there are some more powerful tools which will do the functional analysis as well. And it tends to split down that way. Integrity checking is certainly easier to do than functional static analysis. This type of work is normally tool supported. I think the only thing I can think of that's not a tool supported static technique would be a code walkthrough or a Fagan inspection, something like that. You're not actually executing the software in a code walkthrough, you're doing a desktop review of it. So that would be pretty much the only example I can think of that's not tool supported. But some examples here of the types of things that tools do. Firstly, most compilers have got some static analysis built into them. Compilers will tell you if your variable is being used when it's uninitialized and so on. And so I strongly recommend that you turn on those checks that the compiler can do. A lot of people get a bit confused about the number of warnings that can come out of the compiler and tend to resolve that issue by turning off the warnings in the compiler. That's not good practice. Write your code so that the warnings go away. It's the best thing to do. The second one is what I call heuristic tools. And these are tools which will find some instances of certain classes of fault, but don't guarantee to find all of them in the code. So for example, an uninitialized variable, it can be quite difficult to actually check whether the variables had a value written into it before it's read. Certainly if you've got complex loops in the code and then you read variable output at the end of it, that can be quite a tricky proof to actually perform. So the tools tend to split into two here. Some of them will say, oh, there might be an error here, but not actually tell you definitively whether there is or not. And some of the more advanced tools will actually go that little bit further and tell you definitively whether there genuinely is a fault or not. And the final approach is the formal verification approach. Now this is a really rigorous and powerful technique that constructs essentially a mathematical proof that the software is free of certain classes of error I've written there. Essentially you write some properties of the software and then the formal verification tools can prove that those properties actually are held by the software. So you can, with that approach, pretty much guarantee that there are no faults in your code. Now, as you go through those three types of techniques, the cost and the difficulty of doing that type of analysis increases. So just running your compiler checks is pretty straightforward. Doing the formal verification can be quite expensive and difficult to do, particularly if you write the code first and then try to verify it afterwards. That can be quite tricky to do. So what are the benefits of doing this? Why don't we just sort of do a bit of testing and recognize there's a bit of risk involved in that and live with it? Well, my argument is that the tools these days are pretty quick to run. This was not true 15, 20 years ago. They were quite painful and certain analysis runs could take hours to do. These days they take seconds, so why not use it anyway? It's automated, runs quickly. Why not run a code checker like the clockwork tool that is being demonstrated outside over your software? Static analysis is objective. When you're writing test cases, it's quite easy to fall into the trap of assuming that the code works correctly. So you can write your expected results for a test by looking at the documentation, perhaps even looking at the code in some cases, and fall into the trap of thinking, yeah, this is okay. With static analysis, that's not the case. Because the checks are automated, you will get results out there, and it is not subject to any bias that the tester may have. The third point, the coverage of static analysis techniques. This is one of the main selling points for it. The analysis can cover all the paths through the code and all possible combinations of input. And with a good static analysis tool, that's actually built into the process. So these difficulties that we saw earlier with large combinations of inputs and large number of paths, it all goes away with static analysis tools. And finally, the process is repeatable and auditable. You can, obviously, once you've run your tool over the code, you get some results out. That is easily repeated in no time at all. And the tools will give you good auditable evidence. So it's good practice for verification techniques to be repeatable, auditable, and traceable, and all of that comes pretty much free with the techniques in static analysis. Where is it used? It's been around for quite a number of years now, 30 years or so, these techniques. And it is used in certain sort of pockets of industry. There are certain other areas which don't use it and rely on testing, but there are sort of areas where static analysis is quite common. There's a government initiative around at the moment that's been around for about 18 months or so, called the Trusted Software Initiative. And this is a Cabinet Office initiative to mainly look at improved software quality, and that the reason they're concerned about that is obviously cyber security. It's got a lot of focus up at the cabinet level at the moment. So the Trusted Software Initiative, a guy called Ian Bryant is leading on that, and they've got a pretty good website. Ian told me if I could get one thing through to the software industry, it would be turn on your compiler warnings and get rid of them. And if he manages to achieve that before he retires, he will retire a happy man. On the cyber issue, everyone keeps telling me the main risk in cyber security for software is buffer overflow and buffer overruns. This is where you've declared a certain amount of area of memory in your code, and there are vulnerabilities if your software lets you access outside of that memory that's been reserved. Static analysis can tell you whether that's going to happen pretty easily. This is not a difficult thing to check statically. And that must have some benefits in cybersecurity. So there's another opportunity for static analysis. There's a thing called SWAMP, which the Americans have kicked off. I can't quite remember what it stands for, software, something or other, but it's all about promoting the use of static analysis tools in the cybersecurity area. And there's a lot of American government money going into SWAMP. There's another thing called BOG, which has been kicked off, the British Observer Group for what the SWAMP is doing. And again, this is my friend Ian Bryant at the Trusted Software Initiative who's involved in that. So there's a lot of work going on between the US and the UK in this area of using static analysis to try and improve the situation with regards to cybersecurity. Finally, safety critical systems. Static analysis has been used for many years in the nuclear power sector. The regulator, the Office for Nuclear Regulation, likes static analysis as an independent check that the safety systems in nuclear power plants are doing the right sort of thing. So they have a requirement that the safety critical systems in nuclear power plants are analysed statically, and they prefer for the most critical systems that the whole formal verification approach is used. In the railway industry, the railway standard Senelec 50128 highly recommends static analysis techniques for the most safety critical systems. So when you're in the safety area, these techniques are accepted techniques by regulated industries for giving you the type of confidence that you want in your software-based systems. The MALPAS static analysis tool is an example of a formal verification tool which Atkins actually develops itself and does all the maintenance and marketing of. It's a formal software verification tool. So as I was saying, this is one of the most rigorous techniques that are available. And it does the functional analysis and the runtime error checking, so the integrity checking that I was talking about earlier. It does both of those. The tool is independent of programming language. So regardless of whether your programming language program is written in C or Ada or any other programming language, you can still use this tool to actually verify it. And it's been used for many years now in defense and nuclear systems. Just a little bit of background about it. It was originally developed as a Ministry of Defence research project in the 1980s. There was an initiative by the MOD back then to commercialise some of the software products that have been coming out of their research programs. So Atkins acquired the rights to sell licenses and develop the tool back then. It is the pretty much the de facto tool for verification of safety critical systems in nuclear power plants in the UK. The regulator's guidance talks about using the MALPAS tool. And it's also widely used in defence and rail as well. And all of the claims I've been saying about static analysis are true for MALPAS. It can improve the integrity of your system by giving you very good confidence that there are no faults in your software. It can provide the evidence to demonstrate to regulators that that is so, which is an important point as well. It can provide evidence that then forms part of the safety case for software. and it can help to create software more cost effectively, so in terms of delivering on time and within budget, by identifying faults in the code at an early stage before you've gone through to final testing. And as we all know, that the earlier you find faults in your system, the cheaper and quicker it is to rectify those problems. And the final point is there's also a use of the MALPAS tool to actually prove that the executable software is free of malware. There's a separate presentation I do. I won't go into too much detail today on that, but there's a separate presentation about that technique, and there's a number of published papers as well. This is how MALPAS works. If we start at the top left-hand corner, with the source code that's been written. So this is a static analysis technique that assumes that the source code has been written. The first stage is to translate that source code into MALPAS intermediate language. This is the language-independent input that the MALPAS tool uses. And there are a number of automatic translators that do that. The MALPAS tool itself is made up of a suite of individual analysis tools. These are the control flow tool, data use and information flow are the first three. And these are checking properties such as, have you got sensible use of go-tos in your code? Have you got any uninitialized variables? What inputs do all the outputs depend on? And are there any unusual properties of those? So those first three analyzers are pretty quick to run. You run the tool and you get a list of errors in the software from that. The other two analysis tools in the suite are called the semantic analyzer and the compliance analyzer. These are the ones which actually do the functional analysis for you. So it's checking that the code and the specification are consistent. The semantic analyzer is the easier one to use. So you run the code through the semantic analyzer and have the specification available, and you can check the output from the semantic analyzer manually against the specification, and it will reveal certain classes of error and discrepancies between the two. The second approach, which is the more rigorous approach, is the compliance analyzer, and this will do a formal proof that the code and the specification are consistent. Now, the intermediate stage in doing that is that the specification that you have for the software has to be converted into what we call a post condition. And this is a mathematical representation of what the specification is. There is a sort of condition on this type of analysis that you have to have a pretty good specification for your code, and it has to be consistent and well formed before this type of analysis is possible. One thing that we do find when we're doing compliance analysis is that quite often we go back to our customer who's developed the software and said, your specification is not good enough to do this type of analysis, and then can work with them to actually tease out what they really intended the software to do. It's very easy when you're writing a specification, particularly in English language, to be ambiguous in that specification, and that's bad news for safety critical systems. Excuse me. And then the final output from the compliance analyzer is a threat expression. And this is something which tells you the input values under which circumstances the code does not conform to its specification. And the threat is quite useful in that respect, because you can then generate test cases to put into your software, test it, and then get some really good evidence that you can show to management and to regulators saying, hey, this isn't working under these particular circumstances. So you can actually, rather than just having quite a dry mathematical expression to show them, you can actually demonstrate it on the test rig or whatever. So it's very good for identifying test cases that will break your software. I've got a very short example and a very almost an artificial example but just to give you a feel of the power of the tool. This is a little bit of C code here. You might notice, those that are familiar with C, that I've got a use of pointers in here. Pointers is a classic thing for tripping up static analysis tools, and also in test tools, and when you're doing code walkthrough, it can be quite difficult to actually track what's happening through the flow of pointers. And the other thing about this is I've got a procedure proc1, which is putting a value of 3 into the variable C here. I then call that from proc2, and I want to prove after I've called proc2 that the variable C holds the value of 3. The reason I've done this example like this is just to demonstrate that these tools can actually dig into the analysis, into the software program, and actually prove properties across a number of functions in the code. It's not restricted to just isolating a particular unit of the code. You can actually flow properties through the whole entirety of the program. So there's my C. If you remember from the previous slide, the first thing you do with MALPAS analysis is to translate the code. This is what it looks like. You may not be able to read all of this, but there are some key points to bring out. Firstly, I got a little pointer. Fantastic. Up here, the translation has resolved some of the pointer issues here. So where we were using pointers and address of in the code, it's actually resolved those issues in the translation process. So you can see what's going on in the code rather than just seeing sort of the abstraction at the pointer level. The second thing to note is I've added post conditions here manually to say this is what I want to prove from my software, that the final value of the variable C is equal to 3. I run that through the tool, and this is the output I get. The key thing here is that all threats are false. If you remember, the threat is the expression that comes out saying whether there are any input values under which circumstances the code doesn't meet its specification. Because I've got false coming out, it means everything's okay in this circumstance. When you've got faults in the code and bugs in the code, you get a sort of mathematical expression coming out here, which tells you the input values, under which case the code will not work. So the fact we've got all threats are false there means great, everything's okay. So something just to take away there, and I'm running out of time, is that these static analysis tools these days are very powerful. They can work with code with pointers in, they can work on code that is multitasking and multi-threaded, they can work across many functions within the code and really dig into the detail of the code and prove quite complex properties across the entirety of the program. And for that reason you get a huge amount of confidence at the end of this process as to whether your code is working correctly or not. That's of use traditionally in safety critical industries where you need that high level of confidence, but these tools are so quick to run now, and this particular example took well under a tenth of a second to run. These tools are so quick now that my claim is, why not use them anyway? We've got some tool vendors out there today with some good static analysis tools. Try them out, try these techniques. It can improve the quality of your software. It can save you huge test efforts and late identification of faults in your code. So there we go. That was it. So, thank you.
Thanks. Hi. You say you can cope with multitasking.
Yes.
Can you cope with things like race conditions? Would it detect that, or does it treat them as sort of separate?
Yeah, the tool that we use for multitasking, I mean, MALPAS tool itself doesn't cope with multitasking. It's all about sequential bits of code. But we've got a process which integrates MALPAS with a tool called Spin, which was developed by Bell Labs in the States. And that tool can identify race conditions and such like, sort of this event happens before that one, so that task switches in and all of this sort of thing. And that sort of integration of those two approaches is really quite good, and it's what we're proposing to use on the new power stations for nuclear, because the systems they're using there are multitasking, not heavily multitasking, but they've got more than one task and there is some communication between them. So obviously they need some confidence. We won't get deadlock and all of these sorts of issues arising. So yeah.
Okay, thank you very much, Chris. Thank you.
Thanks.